Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at question 1 from a paper 5, and this is specifically the paper 5 variant 1 from summer 2023. That's May-June exam series 2023. So in this video, I'll just go over question 1, and in the upcoming video, I'll go over question 2 from the paper. And I chose these papers because they are the most recent, and so they might be more relevant if you're writing exams in 2024, but also the questions were fairly challenging, so it's a good paper to work with, preparing for your paper 5 physics, A-Level Physics exam. So if you look at the description below, I will have a copy of this paper with the mark scheme, but my suggestion, like always, is to work on the question on your own before you use this video or use the mark scheme, and make sure you don't have the mark scheme open when you're working with this question, as can lead to some bias when solving the problem. So try to solve it on your own and see how you do, and then use this as a guide if you get stuck or get lost. So we are told in question 1 that a wooden cube of mass A is placed on an inclined plane, and the cube is attached to a cylinder of mass B using a string that passes over a pulley as shown in figure 1.1. The angle between the plane and the horizontal surface is theta. Initially the cylinder is at rest, and the cylinder is then released, and the time for it to fall a distance d we call t. It is suggested that t is related to theta by the relationship 2d over t squared is equal to minus ah sine theta over a plus b minus ka over a plus b, where h and k are constants. We are to plan a lab experiment to test the relationship between t and theta, and draw a diagram showing the arrangement of your equipment, explaining how the results can be used to determine values for h and k, and we need to include in our plan the procedure, the measurements, the controller variables, the analysis of data, and any safety precautions. So the structure of the question, paper 5 question 1, doesn't change. The question itself does, and the experiment and the branch of physics in which the experiment does change. So what am I basically doing here? Well, if I look at this scenario, I need to set up an experiment. Remember, for question 1, think of it as you are writing a guide for someone who is going to walk into the lab and carry out this experiment, and they need at the end of the experiment to prove this mathematical relationship is true or not. And the more information you give this person going into the lab, maybe it's your friend, the better and easier it would be for them to actually carry out this experiment. So don't leave anything out. If you feel something will reduce uncertainty, if you feel something needs to be done for the experiment to be carried out well, with accuracy and precision, then write it down. There's more than enough space for you to include all of your thoughts, including safety precautions and so on. So basically what we're doing is we're adjusting the angle of the plane, and we're dropping the cylinder, and the cylinder's height above the bench, above the horizontal surface here, is always constant. It must be d. And the time it takes to fall is t. And as I adjust the angle, it is suggested that the time it takes to fall differs. And so we don't need to think about the kinematics or the dynamics of the problem. The equation is given. We need to figure out how can we adjust theta and measure the time t for the cylinder to fall. And so the first thing you always need to do is to draw your diagram. Again, if someone's walking into a lab to set up this experiment, they need a diagram so that they have an idea of what you're setting out to do. So I've already drawn this diagram, and obviously this will take you time. This is not something that will magically just appear, but this is, again, something simple, two-dimensional, side-on, and it's something that you need to be able to draw on your own in a very short space of time. And so this is what my diagram looks like. Also, your diagram will not have colors in it, just be drawn in pencil, but I use the colors just so you can see the different parts and the aspects of the diagram sticking out. So what I need is I need to be able to have an inclined plane held fixed and held stationary, and at some angle theta, I should be able to measure the time t it takes for the cylinder to fall. And so what I'm going to use Well, the first thing I need is my flat horizontal bench or desktop. I'm just going to label it bench. Remember to label everything that you use. I then think that a retort stand will be a good idea to hold my plane. Some maybe wooden inclined plane, doesn't really matter. I can simply label it as inclined plane, or plane is fine. And you can see I have my cube on the plane. They've labeled it as cube, so I'm going to say this is a cube. It doesn't really matter what the material of the cube is for now. I've also got a string attaching the cube to the cylinder, and this goes around a pulley. So I'm just labeling everything. Now, it might be a lot to label, but I would suggest labeling everything. I then have a ruler to measure the distance d from the bottom of the cylinder to the bench, but actually I'm not going to let the cylinder fall onto the bench because that's dangerous. I can damage the cylinder or I can injure myself. And so what I'm going to do is I'm going to include a sand box or a sand tray to remove some of the energy when the cylinder falls and prevent it from breaking or damaging anything. The angle theta is the thing I'm going to measure as well, which is nice to have. If I can write the thing I'm going to measure in and display it graphically, by all means, I'm going to do that. I also have a clamp holding the ruler in place, so I'm going to label the clamp. So the clamp is going to, I actually have 2 rods and 2 clamps on my retort stand, which is perfectly fine. One to hold the ruler in place vertically to make measuring D a lot easier. I can even add a demarcation on the ruler if I wanted to. And then another clamp to hold the plane in place at a fixed angle theta. I could even add some blue tack to the bottom end of the ramp, to the inclined plane, to make sure it's attached, it's fixed firmly onto the bench. Not totally necessary. And importantly, I need to measure the angle theta, so I need a large protractor, or if you wanted to, you could draw an inclinometer. That's completely up to you, but a large protractor would do the job. If you had a digital inclinometer, by all means use that as well. And I'm trying to see if I've labeled everything. I think I have labeled everything. But now you can see the person who you have set this experiment up for, who's going to walk into the lab, has a lot easier task. I mean, this is almost good enough for them to walk into the lab and carry out the experiment. And so now that I have my diagram, and now not everything you draw here is going to get you a mark, but it's going to give the marker an idea that you know exactly what you set out to accomplish. So the first thing I'm going to do when I start writing about the things I want to accomplish is I need to define the problem. Basically, now I'm setting out my answers like this because this is how they're set out in the mark scheme. Again, you're going to write more of a story rather than itemizing or listing things in sort of bullet points as I'm doing. But I'm just doing this to show you where the marks are allocated. But the first thing I enjoy doing is defining the problem. I want to tell the person who's doing the experiment what is the independent variable and what is the dependent variable. Now, the independent variable is the thing that I'm changing, and the dependent variable is going to change because I'm changing something else. So what am I changing here? Well, I can change the angle theta. I can adjust the plane so that I have the angle theta that I want. I could make it 10-degree intervals. And so if you spell like me, you're going to be in trouble. But the independent variable, and again, you're going to write this in full sentences, but I'm just writing it in very short form. The independent variable is theta. That obviously means that the time t that it takes for the cylinder to fall at distance d will be the dependent variable. And so the dependent variable is t. How long it takes the cylinder to fall depends on what angle of theta I choose. And then you label all of your constants. So everything you think needs to remain constant, you'll write it down. The distance d has to remain constant. If not, then we're not measuring the relationship between theta and t. the distance d, and also, importantly, the masses A and B, the mass of the cube and the mass of the cylinder, masses A and B must remain constant. Again, you don't have to write this here. You could write this later on in your story, in your guide of how we're going to carry out this experiment, but masses A and B are constant. If you think anything else should remain constant, then you can write it down. The material of the plane, the cube, the cylinder, kind of infer that we're using the same cube and same cylinder and so on. So now that I've defined the problem, I need to talk about the method that's going to be suitable. How am I going to carry out the experiment? And again, if you aren't completely convinced about how you want to set up your method, then write everything you would need in order for you to carry out this experiment successfully. What do you think would be important for this experiment to be carried out precisely and accurately? So the first thing I'm going to do, and a lot of the things that you've drawn in the diagram are self-explanatory, and so you could even sort of maybe brush over them very quickly in the method. But I'm going to measure the angle, and I'm going to use theta. I'm going to measure the angle theta with a large protractor. I can even start by saying, I should start by saying, set up the apparatus as shown in the diagram, which is a good way to start before you even take any measurements. And measure the time t for the mass B, or you can say for the cylinder, to fall a distance d into the sand tray or sand box. And what I'm going to use to measure this is a stopwatch. Now, you don't need to use a stopwatch. You could use a light gate and a timer attached to the light gate, or you could use a video and play it back frame by frame, slow motion, to measure the time. But a stopwatch is fine. There's nothing wrong with the stopwatch. Yes, there is uncertainty in a stopwatch, but again, you walk into a lab and don't necessarily have a light gate on you. So using a stopwatch to measure the time is fine, but we'll see later on that there's a way you can still use a stopwatch and reduce the uncertainty if you use a stopwatch. So now that I have one value for theta and t, I'm going to vary the angle theta, and for each value of theta, measure the value of t. And I'm going to do this for 6 different values of theta, or multiple values, many different values of theta. I want to get as many readings as possible. Why would I want to do this? Is because I want to tabulate the results that I get as follows. Now, the way you're going to tabulate results, you don't have to actually put values into the table, but the way you're going to tabulate your results will depend on what you're going to be plotting on your axes. So I'll show you how I'm going to tabulate my results once I have my 6 sets of readings. So you don't need 6 rows, you just need to show us what the column headings are going to be. Now, the first thing I'm doing is choosing the angle theta, and I'm going to measure that in degrees. So I'm going to have a slash and a degree sign. And if I look at this equation, t and theta are the 2 variables, but I'm not going to plot a graph of t against theta, because then I have a t squared and a sine theta, and the relationship's not going to be a straight line. So in order to linearize it, I'd rather plot a graph of sine theta and 1 over t squared. So what I will need is a column for sine theta now that I have theta. So sine theta, remember this is dimensionless, so there are no units. And then I want to calculate the time. So I will have a column for t1, my first reading for time, column for t2, second reading for time, and then a column for the average time to, again, reduce the uncertainty, take 2 readings and average. Also, I need a unit which I'm going to use as seconds, and then finally, since I'm plotting 1 over t squared on one of the axes, I'm going to need a column for 1 over t squared, and the unit for that will be second to the minus 2. So now I'm also giving the person who's going to carry out the experiment some information. They already know what values they need to take, what readings they need to take, and what units they're going to measure those readings in. And so this is doing a lot of the work for them, making their life a lot easier. And so that's what my table is going to look like. Now that I know what the table is going to look like, I can talk about the analysis. So the analysis is how I'm going to look at my data and analyze it. So analysis of data is hugely important. And you do a lot more analysis in question 2, but we'll just talk about what this person needs to do in order to analyze the data. So I always like writing the equation down. 1 over t squared is equal to minus, and writing it in a way that makes it easier for me to linearize it. So minus a over h divided by 2d into a plus b, and all this multiplied by sine theta. See, I left the sine theta on its own, minus k a over 2d into a plus b. Now, the reason why I wrote the equation in this way is so it's easier for me to write out how I'm going to plot my graph. So what I'm going to do is I'm going to plot a graph. Now, my dependent variable always goes on the y-axis. So I'm going to plot a graph of 1 over t squared. I'm going to say on the y-axis and sine of theta on the x-axis. And if this equation actually does hold true, the suggested relationship will be true if the graph is a straight line, because it fits the form of a straight line. So the suggested relationship is valid if the graph is a straight line. And it's not going to pass through the origin because I have a y-intercept here. So actually, let me just write this down, maybe in a different color. That's going to be on the y-axis. Sine theta is going to be on the x-axis. The thingy in front of sine theta is going to be the gradient, and the term on its own is going to be the y-intercept. It's always good to just make a note of that so you don't make an error. So what I need to do now is, they asked me specifically, mathematically, can you tell us how we're going to find values for h and k, these two constants? Well, I can use the graph that I draw once I have my values of 1 over t squared and sine theta to actually find k and h. A and b are known, and we'll see later on how we get to know them. But the gradient, like I've mentioned above, gradient is equal to minus AH divided by 2D into A plus B. How does this help me? Well, A and B are known. D is also known. I'm measuring D. The only unknown here is H because I can find the gradient of the graph, which means I can use all this information to solve for the unknown constant H. So H is minus 2D times the gradient times A plus B divided by A. And so this is the way I would find the constant H. Whatever this constant is, I can find it because everything else is known. So H is fine, but what about K? Well, I can use the y-intercept. Usually the gradient gives us one constant, the y-intercept gives us the other. It's not always the case, but it's a usual thing with these kinds of questions. Now the y-intercept is minus Ka, if we look above, over 2D into A plus B. So that means I read off the y-intercept from the graph, or I calculate the y-intercept, mathematically, meaning I can solve for k. So k is going to be minus 2d multiplied by whatever the value of the y-intercept is, multiplied by a plus b, all of this divided by a. So I have now shown how I can find the values h and k. You always need to show how to find these values. They will ask you to tell them explicitly. Simply saying gradient is minus ah over 2d into a plus b is not enough. You have to rearrange and show h on its own. Same for the value of k. Simply saying that the y-intercept is minus ka over 2d into a plus b is not enough. Rearrange that equation and show us how you will solve for the constants h and k. Now, the last thing I need to do is actually the additional details and safety precautions. So some of the things I didn't mention, which again would be mentioned usually earlier on, but I'm going to mention now, will score you maybe a maximum of like 6 marks in a question. Although there may be more than 6 points that will score you those marks. So there's opportunities to score very well in this question because there are more marks available. So usually you just need one safety consideration. I wouldn't suggest writing 3 or 4 or 5 safety considerations. And write the one that's most relevant. Well, in this case, we have a heavy mass, which is the cylinder, which could be metal, falling to the table. It could break, it could shatter, it could fall onto the floor, it could injure someone. So how do we prevent that? Well, as you've seen in the diagram, I said use a sand tray. I'll write these as point form, but again, you're not going to write them as a point form. You're going to write them as part of your method. Use a sand tray to capture or catch, I think capture, that's fine, to catch the cylinder capture the, should say more specifically, capture the falling cylinder when the cylinder is falling, and to prevent injury or to prevent damaging the sand tray. So that's one of the most relevant safety precautions. We don't really need things like gloves and so on here, or goggles, but we do want to prevent the cylinder from bouncing off the table or falling onto the floor. So a sand tray or even some foam or something to catch the falling cylinder. Another thing was talking about A and B. We said A and B are known, but we never mentioned how we know A and B. Well, you can use masses of known mass. You can use a cube and a cylinder of known mass. Or even better, to be a good scientist, you'd use a top pan balance to measure the masses A and B. I can simply say A and B. Those are the masses, A and B. What about holding the cube in place? You know, if you are using one hand to set up the experiment and then you have to use another hand to release the cube, it's not going to be the most accurate experiment. So what you can do is use a wedge or a set square, or whatever is more comfortable for you, but you can use either a wedge or a set square to hold the cube in place and move it to release the cube and hence release the cylinder and be able to take the reading. Move the set square or the wedge to release the cube. What else can we do? Well, like I said, but I didn't actually draw, I think it might be good to draw this in your diagram, is use a fixed marker. Use a fixed marker on the ruler or on the bench as well, on ruler, or on the plane, sorry, and plane, to ensure that D is constant. Now, there's many different ways you can ensure D is constant. Make sure it makes sense and it's logical. But any way that you can determine keeping some sort of fiduciary to make sure that the distance D is constant, again, reducing uncertainty and allowing it to be an easier setup for whoever's going to go into the lab and do this experiment. Now, I did say that I'm going to mention a way that using a stopwatch, we can still use a stopwatch with some sort of confidence, and that's by using a large value for d. Use a large value of d. What does this do? This means that if your reaction time error is 0.2 seconds, for example, if you're measuring a larger time, then a large value of d will increase the value of time and hence reduce the percentage or the fractional uncertainty in measuring the time. If you're measuring a very small time with an uncertainty of 0.2 seconds, then you don't have a very accurate measure of time. But if it's a very large time, 0.2 over a large number is a smaller fraction. So you use a large value of d to increase t, and what this does is this reduces percentage uncertainty in the value of t. Absolute uncertainty might remain, but the percentage uncertainty will not. And something I wrote in the table that I didn't mention explicitly, also good to mention explicitly, is to take multiple readings of t, but for the same value of theta. And then take the average. You'll average the values of the time t for the same value of theta, and you'll reduce some of the uncertainty in those values. Measuring time is always a fairly uncertain thing to do, and so whenever you can do some correction by taking extra readings, etc., then do it. Especially in this case where it's very difficult to tell the time where the cylinder first hits the sand tray. And so besides human error, just judging, or rather besides reaction time, just human error in judging the point at which the cylinder first hits the sand tray may be difficult. Hence, you want to take multiple readings of the value of time. It's not an easy measurement of time to make, so make multiple readings and then average them. And so these are some of the additional details. Now, there are others that we included, like the suggested relationship is valid if the graph is a straight line. Sometimes you get a mark for rearranging the equation and doing the mathematics correctly. There are also additional detail marks included in our diagram, included in maybe saying a large protractor rather than just a protractor. So there are small things that we can say that will include marks for additional details, but there's a limit to the number of marks that you can score for additional details and safety considerations. But altogether, this question is worth 15 marks, and you can see that there are more than 15 marks available. So if you use your techniques, your lab techniques and methods that serve you well, then you should be able to come up with something that will score you many of these marks that are awarded. So read the question carefully, but you need to be effective as well as efficient, as you don't have much time to answer this question because the entire paper is just an hour, 15 minutes. And so you're going to have just over half an hour for this question. So being able to draw the diagrams neatly with the ruler, with the pencil, and quickly is as important as understanding the concept and how to answer the question. And so in the next video, I will do question 2 from this paper, which is the analysis and evaluation, if this was the design of the experiment. And that's all for me, Mr. K, for now. I'll see you again next time on Everything is Relative.